Today we turn our attention to the graph of the function y equals k times x squared. This is the direct variation equation that states y varies directly with the square of x. So you'll notice a few differences as you explored in your exploration today, that as k gets larger and stays positive, the sides of this parabola actually are being pulled vertically. It's being stretched up, but it gives it this effect that it's actually pinching in towards that y-axis. Now, as k's value gets less and less, but stays positive, so in other words, as it gets closer to 0, in between 1 and 0, you should see that the sides of this parabola start to fall towards that x-axis. In other words, it looks like it's widening out. Then as soon as k gets negative, it takes that parabola and reflects it over that x-axis. So now it's a parabola that opens down instead of opening up. And again, as that value gets larger and larger in the negative direction, then it looks like it has that effect of pinching towards that y-axis. Similar to the graph of y equals k times x, all of these graphs pass through the origin. And they are all going to be symmetric about the y-axis. So you can see here that this parabola here passes through our origin, and the y-axis comes through and acts as a line of symmetry. In other words, this is reflection symmetric. If we were to fold this graph over the y-axis, then this side of the parabola would fall on top of the other side of the parabola. So these are just a few things that you guys should have picked up from your little exploration. Let's jump into a few examples. In example 1, we are given that the braking distance can be modeled by the following function. The distance it takes to stop is equal to 1 over 20 times the square of the speed the vehicle is moving. Now, it says find the following rates of change. Well, rates of change, remember, mean slope. So we need to use 2 points here. The 2 points that they give us are 10, 5, and 20, 20. So we'll go ahead and calculate that slope. And that represents 1.5, and that is going to be feet per mile per hour. In other words, for every increase mile per hour, it's going to take you 1.5 feet to stop. All right, now let's calculate the rate of change between 2020 and 50/125. On the graph, that's this point here and 50/125. That point there. So we're now finding the rate of change, or the slope, between those 2 points. Whereas before we found the slope between 10, 5 and 20, 20. And that comes out to be 3.5 feet per mile per hour. So you can see here, as our speed is increasing, it's going to take us longer to stop. In other words, 3.5 more feet per 1 mile per hour increase. So you can see why this is not a linear function, but this is more of this gradually increasing function here. So we note that the rate of change between two different pairs of points are not constant. 1.5 and 3.5 are very different. They're not the same. Therefore, the graph of this function is not a straight line. It's not linear. Therefore, it can't be modeled by y equals k times x. We see here, actually, it's modeled by y equals k times x squared. Or in this case, d equals 1 over 20 times s squared. So therefore, a single number does not describe the slope of this graph. All right, let's take a look at one more example. We want to consider the function y equals k times x squared. Again, that's a direct variation equation. We have it graphed over here on the right-hand side. We also have 2 sets of points. We see it passes through the origin. The y-axis is my line of symmetry. We have a parabola that opens up. Therefore, my k value, I know, has to be greater than 0. must be positive, in other words, because if it were to open down, then my k value would be negative or less than 0. Anyways, it asks use the points to find the value of k and give the equation for this function. So we're actually going to use the point 2a because we can't really use 0, 0. And remember, anytime we know one relation, we can find the equation if we know the model. In this case, our model is k times x squared. So let's substitute the values in for k and y. So 8 is equal to k times 2 squared. 2 squared is 4, so that's k times 4 is equal to 8. Divide both sides by 4, and I have a value of k to be equal to 2. Now let's rewrite that equation as y equals 2 times x squared. And this is my direct variation equation that models this curve.